I posted these slides there, so if you want to follow along on your own device, you can do that. So today I'm going to talk to you about building cross-platform applications leveraging WebAssembly. But before doing that, I'd like to make a quick detour to an even more important topic, tea. I really, really like tea, and this hobby and addiction kind of made me realize how similar tea is to new technologies. You see, when you try a new tea, the first thing you notice about it is the taste. That's your first point of contact. But then as you keep drinking it, you start to wonder, where did it grow? When was it picked? How was it processed? And as you get even more into it, you start to think about, okay, how do I feel after drinking this certain type of tea? And the same goes for new technologies. If you come to a conference or read a blog post or watch a video on YouTube, the first thing you'll learn about a given technology is how to use it. That's your first point of contact. But then as you get more interested, you start to wonder, okay, who's behind this technology? Who created it? How does it work under the hood? And as you get even more into it, you start to wonder, how will this affect my code base? How will this affect my team? Maybe the hiring process. So there are many things that you only consider later on. Like I said, I'm going to talk to you about building cross-platform applications using WebAssembly. And although I'm going to touch all these three phases, I'm going to focus a little bit more on the third one. How do you feel if you choose this architecture? How will it affect your code base? How will it affect your team? But obviously, we can't really talk about anything WebAssembly related without answering the question, what is WebAssembly? Well, Brendan Eich, the inventor of JavaScript, posted on Twitter a definition. I'm not even going to read it. It's obviously a joke, but I really like how it shows that there are many, many ways to define what WebAssembly is. To go with a shorter, more simpler one, you could say that WebAssembly is a binary format. Basically, you write a piece of code in C, C++, or Rust, you compile it into WebAssembly, and the browser will be able to run this WebAssembly code. So basically, from now on, the browsers can run JavaScript and WebAssembly. Because it's a binary format, it has the fact that it's a binary format has serious consequences on the performance. So some people refer to WebAssembly as the next step in web performance. It has a lot of cool features that will impact the performance in a positive way. For example, there's no interpretation step. It has consistent performance. You can manage your memory manually and so on. There are a lot of things, and they are all right. So basically, before WebAssembly, the web felt like something that's really, really slow, but a few hacks and tricks, you can make it a bit faster. But with WebAssembly, it's more like a really smooth ride where you just enjoy the speed. Another way to define what WebAssembly is by saying what it's not. First of all, WebAssembly is not a solo mission. All the major browser vendors are behind it, so Google, Microsoft, Mozilla, and Apple, they are all pushing it at the same time, so that's pretty cool and pretty encouraging. Also, it's not the next Java applet. It's not running in a sandbox. It has the same rights as JavaScript. So basically, it will be possible to write a whole web application only using WebAssembly and no JavaScript. And sadly, it's not ready yet. The version that you can use today in your browser is an MVP version. It has feature parity with ASM.js. But really cool additional features are going to come in the next months. So keep watching, because it's going to get better and better. But the definition I like the most was given by Lynn Clark. She said that WebAssembly is a way to run programming languages other than JavaScript on the web. And I think this is, like, performance is really important and really cool, but I think this is even more important, because if you look at it from this point of view, you can take a piece of code that was written for a totally different platform and run it in the browser. That's pretty exciting. So I'd like to tell you the story of Join Me, and through this story, I'd like to tell you how you can write cross-platform applications from this way. Join Me is a product I work on. It's an online conferencing screen sharing tool. It was first released in 2012 for Windows, and it became a success pretty fast, so new platforms followed. First the Mac, then the Android, then the iOS. And then in 2014, the team realized that we needed a web platform. We needed to add it. If this happened today, our first question would be, should we use like one of these JavaScript to native cross-platform applications, like Gregory told us about earlier, React Native or Electron or all these? Well, again, like you heard before, they certainly have a lot of upsides. But also, they have a few drawbacks too. Obviously, it really depends on your situations if these drawbacks are important or not. But a few things to consider, and the few things our team considered were, it's an extra layer of abstraction. And as software engineers, we're always trying to find the right level of abstraction. Sometimes more abstraction is really good, but sometimes it can be a burden, especially if you're striving for good performance. It can make your life harder. Also, choosing a library is pretty easy, because if you don't like it, you can easily switch it out to something else. But choosing an ecosystem is harder, because if you opt in and you start writing your app in it, it's really hard to get out. So it's a more serious commitment. And also, from the HR, from the recruiting point of view, it can be a nightmare. I mean, I don't know about Kiev, but in Budapest, it's really hard to hire one good JavaScript developer. If you want to scale your product and you need 5 new developers, if you want to hire 5 new JavaScript developers, that's almost impossible. So we went a different way. We used a tool called mscripten. Mscripten is a compiler that takes a piece of C++ code and compiles it into JavaScript, more precisely ASM.js. You don't want to see the resulting code. It's really ugly. What mscripten does is basically black magic, but it works. Back in 2014, you could actually run C++ code in the browser. The performance was awful, but it worked. So what they did was basically took out all the common code that could be shared between all these platforms, wrote it in C++, and then shared it. Because you can compile C++ to almost any platform, and thanks to mscripten, you can compile it into JavaScript too. So we had a library really creatively called Common, and all of our platforms were using it, and all of the platforms only had to write their own front ends and nothing else. So that was pretty useful. But you might ask, OK, this mscripten is cool, but what does it have to do with WebAssembly? Well, the thing is that today, they are kind of the same thing. Notice there are only 2 equal signs, not 3. Mscripten today is the official compiler for WebAssembly, meaning if you have a setup like we did, where you're compiling C++ code into JavaScript using mscripten, by changing one single flag, you can make it compile into WebAssembly. So with only a few really minor changes, we could switch from shipping ASM.js code to shipping WebAssembly code. And thanks to these really small changes, and I really have to emphasize how easy it was, we managed to decrease our bundle size by 50%, only by doing this. So WebAssembly is pretty cool, you believe me. We've been working with this approach and this architecture for 4 years. And even though we only switched to WebAssembly a few months back, still, I think we are kind of like the dream of recruiters, because we have 4 years of experience in a technology that's only 1 year old. So I'm going to try to share these experiences we had. I'm going to focus first on the technological side and a bit later on the human side. Yeah, so let's talk about the technological side. So you have a code base, a library that's written in C++. It has the fact that it's written in C++ has a few cool things about it. Like, it's really easy to integrate new platforms. Like, most of the mainstream platforms have a way to run C++ code. So it's really easy to add new ones. And also, it gives you the right amount of freedom, because you're not forcing JavaScript or Kotlin or any other language onto a platform where that's not native. Usually, every platform has the best tools for that given platform to work on to create nice user interfaces and so on. And thanks to C++, we didn't have to do this forcing. All the different platforms could use their own tools, their own languages, whatever they wanted. But also, it has drawbacks too. It's really slow to compile, the CI is really complex, but I think the worst thing is that it has a really high entry barrier for developers. So I don't know about you, but I still have nightmares from back in the university when you had to write a lot of C++ code. At least for me, it's really easy to shoot myself in the foot. Obviously, you can't have a setup where somebody can contribute from day one, but you want to make this process as simple as possible. And if you have a language that's hard to get started with without experience, that slows you down. But after a bit of time that we spent working with C++, we started to ask ourselves the question, does the language even matter? Because what are you sharing? What would you put in that common library? Basically, the business logic and nothing else. And if you think about it, writing business logic kind of looks the same in every language. A few if statements, a bit of state management, but nothing really extreme, nothing exotic. The other thing that we realized during this process was that you never, ever should put anything else but the business logic in this common place. So if you put anything that's platform-specific, it just opens the gates of hell, and you get spaghetti code in like record time. So please don't do that. Also, if we're talking about sharing code, usually, if you have multiple platforms, the front-end code for these platforms won't be exactly the same. They have different depths. Like on some platforms, you have more features. On the other one, you have the same features, but somehow different. So they won't be exactly the same. But still, you might be tempted to make this common part as thick as possible. In our experience, that's not really a good approach. You should only share things that are definitely, clearly common, and anything else shouldn't be forced. So if you're shipping code on a platform that won't be used at all, you're making your user's life harder for no reason. So what we did was, when we tried to share a bit more code and reduce the cost of bug fixes and so on, was to add another layer of abstraction where it was clearly possible and where it was clearly a good idea, and we left the other parts out. We call it a bacon because it's in the middle, but you can call it whatever you want. And if we're talking about layers, the next question that arises is, how do you connect these layers? Well, obviously, it's really easy. You just plug it in and it works, right? Because usually, plugging things in is really simple, and we're really good at that, making these connections. Yeah, I see some of you are grinning. You must be Mac users. You shouldn't grin. It's the same problem there, too. So basically, for some strange reason, as computer scientists or programmers, we're really, really bad at connecting things. And even if we come up with a solution that works, we should strive for solutions that are better quality and, even more important, safer. And in our case, safer means that we connect these layers in a way that small changes won't cause huge bugs all over. So what do you do in this case? Well, it seems like a common sense, but we kept coming back to this over and over again. The contract must be sacred. Even if it's like a really, really small change in the API and you think nobody will feel this, there's no way to predict what will happen if you have so many different platforms that are dependent on your common code. Even if they use the same API, these different platforms are different words, and the same API could be used in very different ways. So you shouldn't change your API only if you really, really must, and then consider it a really expensive thing and test it really, really well to make sure that you haven't broken anything. Yeah, you could basically automate this testing, because testing is easy, right? Like, you just test it, and then you don't need manual testers, nothing like that. The problem is that you can write as many unit tests as you want. They are really useful in their place, but they won't help you with these connection problems. Okay, it's integrating layers, so you have to write integration tests. That's a good idea. I fully support that. You should do that. But be aware that doing this is really, really expensive, because you have a lot of different platforms, and you have to write these integration tests for each and every platform. And usually, they are really different. Instantiating your code can be really, really tricky in a clean way. So another thing that you may do is say that I don't need integration tests. I just do a few smoke tests in an end-to-end fashion, and that, if that works, the integration is successful, right? Well, the problem is that end-to-end tests are even more expensive. Again, you have a lot of different platforms. You have to test each and every one of them. Each and every one platform has different methods, different technologies for end-to-end testing. And for us, especially, the hardest thing is that if you have an application where different users can use it at the same time from different platforms. For example, in our case, there's a meeting where somebody joins from an Android phone, somebody joins from the browser, and the whole meeting is hosted on Windows. Then you have to test that situation. And there aren't that many tools that will provide you really easy actions for that, like simulating an action from Android, then simulating an action from the browser, and then on the native Windows host. So it's pretty tricky, and every time we thought that we knew how expensive it is, we realized that it's even harder. So if there's one takeaway from all these testing things, is that you have to have a really good CI as early as possible. So I know, again, this is kind of like a common sense that you have to automate as early as possible. But in this case, if you don't do that, you won't be able to scale. You won't be able to add new features. And another reason to do that is that because each platform has different ways to create a new version of the product, to build a new product. And nobody will keep that in mind. Like, nobody will know all the ways. Like, I may be able to remember the actions, how I can build a new web client. But how does it work on Windows? I don't even have a Mac machine. So you have to automate all this, put it somewhere in the cloud, and make it work just on a click of a button. OK, let's talk a bit about the human side. If you have so many different platforms, and it means that you have more than one team, especially if you're growing, if you're scaling. And it's a really hard question. How would you organize? During these 4 years, we tried more than one setup. And for the sake of simplicity, I'm going to tell you about the two extremes. So one end of the spectrum is having feature teams. By feature teams, I mean that this common code has a dedicated team whose sole job is to maintain that code, add new features. And all the front ends have their own dedicated teams too. The other end of the spectrum is more like a Spotify kind of model, a cross-functional team, where you have teams that can touch multiple platforms, multiple code bases, and they can deliver a feature from top to bottom all by themselves. So I'm going to compare these two, but don't get me wrong, the solution is always somewhere in the middle, and we're always experimenting with like mixed approaches, but I think the general ideas will be more clear this way. So first of all, how do people approach their code base in these different organizational models? Well, in feature teams, they feel that they're working on a product. So they have this product mindset where they really, really know their field of expertise, they work really, really fast there. They really care about it. They have ownership. On the other hand, with cross-functional teams, they work with multiple code bases, and the same code base may be touched by multiple teams. So it feels more like working in open source, where you're opening issues and pull requests only when you need something, but you won't do the dirty work, the cleanup, that somebody else will do it. An interesting consequence of these approaches is that the feature teams work a lot faster because they know their code bases. That's what they focused on. So they are a lot faster. While the cross-functional teams, even if they have multiple talents and they know a lot of different code bases, the context switching costs time. So they will be inevitably slower. On the other hand, because with feature teams, you only have one team who's working on this common code base. Even if they are really, really, really fast, still it's possible that there will be queuing because everyone depends on them. In a cross-functional organizational model, there will be no queuing because a team can deliver a feature alone. They don't depend on anyone else. So from a product owner point of view, the feature team is really good because they have ownership. If there's a problem with, I don't know, the Windows client, they know who to turn to. They know who are the people who are able to fix it really, really fast. On the other hand, in the cross-functional organizational model, it's much easier to estimate because there are no dependencies. Even though the work may be slower in total, because the estimations are more precise, product owners will love this organizational model more. So to summarize it, I think in our experience, feature teams are better if you're doing like really large steps, when you're like rewriting a part of the application or adding a bunch of new features. But when things slow down and you have to make smaller steps, cross-functional teams tend to work better. And as a general takeaway, I would say that trust is key. Like, again, common sense. You have to trust your coworkers. But in this scenario, when so many teams depend on each other for a common success, it won't work at all if you go in with the mindset that, yeah, they are not able to code it as I would be. Like they are not doing a really good job. I would do a better job. You shouldn't have that. Especially in the cross-functional organizational model, never. And also, scaling is hard. Again, this could be said for anything, but in this case especially, because whatever organizational model you choose, still adding new features, adding new code will get harder and harder as you go more into it. Also, another lesson we learned the hard way is that if you're communicating to pull requests, that's too late. So if you think that you know a part of the code base and you add a new feature and then open a pull request with it, usually the people who also want to work with that code base will say, no, you have used a totally different approach because this hurts us in a way that you never knew about. So because there are so many dependencies, please communicate earlier. Before you start developing, before you write a single line of code, speak with the other teams, discuss your ideas. It's going to be better this way, I promise. And last but not least, having more diverse teams is always better. But in this case, it was especially good because with this common piece of code, we had multiple backgrounds. It wasn't like if we have used like React Native or Electron, all of the developers have JavaScript backgrounds, so they see the problems in a certain way. But in our case, we had people who had C++ background, Java background, Objective-C background, and so on. A lot of different backgrounds. And this resulted in longer debates. But in my opinion, the solutions that we came up with at the end were a lot better. So let's do a live demo. I could show you how to take a piece of C++ code and compile it, but there are a lot of tutorials for that on the web, so I think I'll show you something a bit more interesting. There's a library called AssemblyScript, and it's made by Daniel Wirtz. I hope I pronounced his name right. You can find him on Twitter under dcode.io. What this library does is basically it's a subset of TypeScript, and it comes with a compiler that compiles your code to WebAssembly. In practice, you write a regular JavaScript function, add a few type annotations, run an npm command, and it will take this JavaScript code and compile it into WebAssembly. So you don't have to know any C, or not even Rust, and you'll be able to start to play with WebAssembly. But it's not only a toy. In some situations, in general, performance is complicated, and WebAssembly performance is even more complicated. But in some situations, you may be able to gain performance by taking a part of your JavaScript code, rewriting it in AssemblyScript, compiling it into WebAssembly, and these few steps may result in much better performance. So let's see how this works. Can you read my code? Is it large enough? So here you can see I have a really simple JavaScript function that calculates the Fibonacci number. It's pretty readable. The only strange thing is that we have these type definitions. Like I said, these come from AssemblyScript, and in this case, I32 is a 32-bit integer. We open the console, and we'll just say ASC, which is AssemblyScript, fibts, the TypeScript file, and compile it into fib.webassembly. Enter, and it's a really fast process. ASC is just an npm package. You install it by npm install AssemblyScript. That's it, no magic there. So how can we test it? Well, we need a really simple website for that. It's an empty website. I have no content here. I just have a script tag. Here I have the same function, but in plain old JavaScript. And also, I have a few lines of black magic where I load the WebAssembly file. Please don't remember this. You'll be able to import WebAssembly files with the @import tag. Right now, it's working like this, but the solution is coming pretty soon. So let's see how this works in a real browser. I have this WebAssembly object, and on it, I have fib, which is a function. Cool, let's call it. WebAssembly.fib. 5 is 8, 6 is 13, so it works, right? Well, let's see what it says if I enter a number that's a bit bigger. Let's see, 200. Wow. I don't think that a Fibonacci number should be negative. Let's test it with the plain old JavaScript one. 200. No, they're not equal. What's happening here? Well, if you've been paying attention, you may have seen that I used 32-bit integers, but JavaScript uses doubles. So what happened here was basically an overflow. But it's really easy to fix that. Just take all these type definitions and replace them with F64, which is basically a double. Obviously, you have to recompile it. And you also have to refresh your page. And you have to refresh your page again. And you have to recompile it again, because second time is the charm, right? Sorry? Anyway, if you use, yeah, it wasn't saved. Come on. Such a rookie mistake. And now I did a typo. Yeah. Any minute now. Save it. Oh, finally. Thank you for your patience there. So you see, they are equal, and I wasn't lying. I was actually running WebAssembly code because I could use different types than what JavaScript has. Okay, let's do another. Let's do something else. If you wanna pass an object to a WebAssembly function, things get more trickier. And to explain it, I use an analogy. I don't know if you know what corruption is, but I'll explain it to you. I'll explain it to you. So basically, you want something done, but the official channels are taking too slow, so slow that it's impossible to get it done. So you just go to someone who can help you, but you're not giving them your money directly. No, 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 no. You just ask for their secret Cayman Islands bank account number. You go home, wire them the money, and then you try the official channels, and for some strange reason, it works. And the thing you want to get done happens. Well, the same needs to be done in WebAssembly, because you can't communicate directly to the stack. You have to use the heap when you're dealing with objects. So let me show you an example. So what I'm trying to do is pass a WebAssembly function an array, and it will add all the numbers in that array and return their sum. So the first thing, I'm creating a test array, and then I need a pointer. What happens here is basically I give the I call a WebAssembly function that takes the length of my array and allocates memory for it, and then returns the pointer itself. So this step is basically where I ask for the Cayman Islands bank account number. The second step is where I actually wire the money, where I actually take my test array and write its content into the heap, into the position that was given by the WebAssembly part. And then I can go through the official channels and just call this some function that will know where to look for our payload, and then it will be able to work with it. So just to show you how it works, basically I say test, and it returns the sum of the elements of the array. So from this, you can see that passing things, and the same, you have to do the same when you want to pass something complicated from WebAssembly to JavaScript. So from this example, you could see that passing things around is pretty complicated, and this is the biggest bottleneck for your performance. Like I said, performance is tricky, and you shouldn't expect any performance gains from WebAssembly if you have a lot of back and forth between the two. So the ideal situation for WebAssembly would be to pass it like something simple, like a number, and then it should do like a lot of computations with it, and then it should pass something simple back, like another number. Obviously, in real world, life is not that easy, but this is something you should consider before expecting any huge performance gains from WebAssembly. The tooling is getting better and better every day. Like this tweet went out yesterday, and it's about an additional feature in Webpack where you just import a C file like regular JavaScript, and you can use it thanks to Webpack and WebAssembly. I think in the long term, these tools are going to get even better, and many of us won't even realize that we're using WebAssembly under the hood. I'd like to close this talk with a thought that Brandon Eich used to close his talks with. he used to say that always bet on JavaScript. And we can see that he was right. And lately, he added one more thing to this. Always bet on JavaScript and WebAssembly. Thank you very much.